Hello and welcome to another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 7, Lesson 9 on recognizing structure to factor. So we've got a couple more lessons in this unit on factoring, and today we're going to look at some more challenging factoring problems. But before we do that, let's review the three major types of factoring we've seen so far, right? So up to this point in time, we've seen three basic types of factoring. One of them, the one that you should always look for first, is greatest common factors. That's when we look at an expression and we look at each term in the expression and we see that each term has got a common factor, right? So 10x and 35, both the 10 and the 35 have a factor of 5, which means we can rewrite 10x minus 35 as 5 times 2x minus 7. All right, we are reversing the distributive property, if you will, there. Now, the second type of factoring that we looked at, let me bring this up just for a moment, was the difference of perfect squares. This one is a real situational one, right? This is when we have a difference, a subtraction, we have a binomial, and both parts of the binomial are a perfect square, all right? They could involve variables, numbers, or both, right? So here I have x times x, x squared, and really for 100 I have 10 times 10, or 10 squared. The difference of perfect squares will always then factor into what are called two conjugate binomials. Binomials that look identical, but at the same time differ between a plus and a minus, a sum and a difference. The final type of factoring that we looked at most recently was trinomial factoring, right? And turning it into the product of two binomials, right? So this is a situation where I have three terms, x squared plus 10x plus 21. In these types, we will always have a leading coefficient of 1. And really remember, what we were always looking for were two numbers that had a sum of this and a product of this, right? So if I think about that, right, two numbers that have a sum of 10 and a product of 21 are positive 3 and positive 7, so this factors into x plus 3 and x plus 7. Now before we move on and look at some more complicated factoring, I'd like to revisit difference of perfect squares given what we know about trinomial factoring. Now, the difference of perfect squares is always with this very specific looking binomial, something squared minus something squared. But at the same time, I could actually turn this into a trinomial by rewriting it as x squared plus 0x minus 100, right? Putting in a 0x doesn't change anything at all. Now, if I think about it in light of what I just said down here, right? I'm looking for two numbers that have a sum of 0 and a product of negative 100, right? Well, those two numbers are 10 and negative 10. There's lots of numbers, of course, that have a product of negative 100, like for instance, 4 and negative 25. The problem is if I do 4 plus negative 25, I get negative 21. I don't get 0, right? So these are the only two numbers that would then have a product of negative 100 and a sum of 0. So it really does fit into the same pattern as this. It just tends to be that people don't have to think very hard about that because it will just simply be x plus 10, x minus 10, right? It'll be whatever that is, the square root of that number. All right, now let's move on. Okay, we will now factor more complex expressions. In each case, we will look for the structure of one of the three main types of factoring. So let's jump into exercise 1, which is actually something that you did as early as Unit 1. Let's take a look. Write each of the following expressions in factored form by factoring out a more complex greatest common factor. Be careful in B with the subtraction. All right, so the structure of these two really is all about GCF. Okay, if I look at letter A, which looks very complicated, I've got x plus 3 times x minus 7 plus x plus 3 times x minus 4. Now normally when we do GCF factoring, we're actually kind of pulling out a monomial, you know, the number 5, or perhaps the expression 7x or something like that. But in this case, it's very obvious that an x plus 3 is multiplying both an x minus 7 and an x minus 4. So I can actually factor this by factoring out an x plus 3. And when I do that, inside of the parentheses, right, when I reverse my distributive property, inside of the parentheses I have x minus 7 plus x minus 4. And again, just think about this for a moment. If I were to start with this, right? If I gave you this and I said, show me the first step if you multiplied this all out, I would hope that you would say, well, I'll multiply x plus 3 times x minus 7, then I'd do plus x plus 3 times x minus 4, which would be exactly what we have here. Now, I want to write this as the product of two binomials. The x plus 3 is done, but I can simplify what's inside of here by employing the associative property of addition. I can simply remove those parentheses, and then I can combine like terms, right? X plus x is 2x, and negative 7 minus 4 is negative 11. And again, very, very important to understand. This expression down here is equivalent to the one up here. If I took any value of x and I threw it into this expression and I got some numerical value out, I threw the same value of x in here, I'd get the same numerical value out. Never forget, with all of these kind of algebraic manipulations with factoring, we are simply rewriting an expression in an equivalent way. All right, now letter B is a little more challenging because of this subtraction, but we've done these before, so I'd like you to pause the video and see if you can work through this one. All right, well, just like in letter A, we have x minus 5, which is a binomial multiplying both of these two. All right, so let's start by factoring that x minus 5 out of this larger expression. Okay. Now again, I want to be very careful. Notice how I'm leaving the parentheses around the 5x plus 2 and the x minus 7. Okay, here comes the tricky part, right? Unlike the addition, when I do a subtraction of this binomial, what I'm really going to do is I'm going to end up adding the opposite of it. So let's pause just for a second, right? So instead of subtracting x minus 7, I'm going to add negative x plus 7. Let me make that look a little bit more like an addition sign. Okay, some teachers will say, well, what I'm doing is I'm distributing the subtraction. That's a little bit weird. And other teachers will say I'm distributing a multiplication by negative 1. That's awesome. Nothing wrong with that, okay? But as we all know, whenever we subtract anything, it's the same as adding its opposite. So subtracting x minus 7 is the same as adding negative x plus 7. The rest of it works out just like this one. I can now combine like terms. I have a 5x and a negative x. That's going to be a 4x. I have a positive 2 and a positive 7. And that's going to be a positive 9. X minus 5 times 4x plus 9. Okay, let's keep working on more structure problems. Now sometimes we will need to use multiple techniques to factor an expression completely. So we did complete factoring actually in the last lesson. And all complete factoring really means is to factor until you can't factor anything anymore, all right? But it's always still going to boil down to one of those three techniques, or two of those three, or maybe 3 out of the 3. Let's take a look at exercise number 2. Factor each of the following expressions completely. Start by factoring out the binomial GCF. All right, cool, let's take a look. So just very, very similar to exercise number 1, when I look at this complicated expression in A, what I see is x squared times x plus 2 plus x plus 2 times 5x minus 24. And immediately what I hope to notice is that this x plus 2 is showing up in terms of these two larger expressions. All right, so I can begin by factoring an x plus 2 out, and then what I'll have here is x squared plus 5x minus 24. Whoops, almost got that. 5x minus 24. And actually, let me be good about putting the parentheses around the 5x minus 24. All right, but right away we should be able to do that, right? X plus 2 is multiplying x squared, and x plus 2 is multiplying 5x minus 24, so we're golden, all right? Now I can remove those parentheses inside of that larger set. Because this is addition, the parentheses do not matter, so I can get rid of them. If it was subtraction, I would have to add the opposite. All right, so now let's talk about what we can do. There is nothing we can do to factor x plus 2. It is done, all right? But this is a trinomial, right? This is a trinomial factoring. So what I now need to do is I now need to factor it into the product of two binomials. Now, what will those two binomials be? Well, I'm looking for two numbers that have a sum of 5 and a product of negative 24. So one of the numbers has got to be positive, one of them's got to be negative, and the larger one has to be positive so that when I add them together, I have a positive sum. I'd like you to pause the video right now and see if you can think of two numbers that have a product of negative 24 and a sum of positive 5. All right, well, those are going to be positive 8 and negative 3, right? 8 times negative 3 is negative 24, and 8 plus negative 3 is positive 5. So we can finish factoring this as x plus 8 and x minus 3. Ah, that's just pretty. There we go. All right. Now, letter B. All right, let's take a look at that together, and then I'm going to have you work on it. Letter B is x squared times x minus 3 minus 8x plus 20 times x minus 3. All right, great. Very similar to before, all right, but just like in exercise 1B, we've got this subtraction to contend with. So I'd like you to pause the video now and see if you can work this all the way down until you have the product of 3 binomials. Pause the video now. All right, first things first, let's factor out that x minus 3. Here we go. All right, I pull out an x minus 3. Inside, I'll have x squared minus 8x plus 20. Now again, very, very important here. Right, I'm now going to add the opposite, or better yet, I'll distribute that subtraction, right? So I'm going to have negative 8x minus 20, right? Both that 8x and that 20 become negative because they're both being subtracted. All right, now I've got this beautiful trinomial. I'm thinking to myself, okay, I've got two numbers that have a product of negative 20 and a sum of negative 8. Just like before, because the product is negative, one number's got to be positive, one number's got to be negative, and the larger of the two numbers has to be negative because their sum is negative 8. So what two numbers have a product of negative 20 and a sum of negative 8? Well, those would be negative 10 and positive 2, right? Negative 10 times positive 2 is negative 20, and negative 10 plus 2 is negative 8. So we'll have x minus 3 times x minus 10 times x plus 2. Now, students will always ask me, well, I had x plus 2 times x minus 10. Is that still correct? Right? So if you had x plus 2 and x minus 10 here, in other words, those two binomials were still there. They were just in the opposite order. The answer is that's perfectly okay. This is multiplication of 3 things. You could have these 3 binomials down in any order you want because multiplication is commutative. All right, let's do some more structure work, get into something that's a little bit different than these. Now, sometimes we will need to look at the overall structure of an expression to see what type of factoring is possible, okay? And these things can definitely get tricky. They love putting tricky ones on exams. For some reason, they think that the basic 3 are too easy for you, even though this is really the first year that you learned difference of perfect squares and trinomial factoring. They will often throw a hard one at you that you have to really recognize structure on an assessment. So let's take a look at one of these in exercise 3. Consider the expression 3x plus 1 squared minus 2x plus 5 squared. Letter A, what type of factoring does the overall structure of the expression suggest is correct, and why? All right, so I'd like you to pause the video now. I'd like you to think about that expression, all right? Look back at our 3 basic types of factoring and ask yourself, which one of those 3 is that most similar to? All right, well look, it's the difference of perfect squares, right? I've got something squared minus something squared, right? So this should immediately kind of say to us, well, this is the difference of perfect squares, right? And it really has the structure something squared minus something squared. So that's going to have to factor into something that looks like this, a plus b times a minus b. All right. The whole point, though, is that the a and the b aren't monomials. They're actually binomials, which makes life a little bit trickier. Let's take a look at letter b. Using your answer to a, factor this expression so that it is the product of two binomials. All right, well, we've got a follow-up one that's very similar to this, so let's do this one together. All right, now remember, it looks just like this. The big difference is a is equal to 3x plus 1, and b is equal to 2x plus 5. So when I factor this now, right, it's going to be a little bit of a squeeze here. We're going to have 3x plus 1 plus 2x plus 5. And let me put parentheses around these. Again, let me be good about that. And then it's going to be 3x plus 1 minus 2x plus 5. All right, we really need to look at things in parentheses sometimes as if they're no different than a single variable or a single number. I should be treating this no different than x squared minus 100. Right? If x squared minus 100 is x minus 10 times x plus 10, then this squared minus this squared should be this plus this times this minus this. Now this one's going to be, again, pretty easy. This one's a little bit trickier because of the subtraction, but let's get rid of those parentheses. Okay, in this case, we'd have 3x plus 1 plus 2x plus 5. In this case, we'll have 3x plus 1 minus 2x minus 5, distributing that subtraction. Now it's just combining like terms. 3x and 2x is 5x. 1 plus 5 is 6. And in this case, 3x minus 2x is just x, and 1 minus 5 is negative 4. 5x plus 6 times x minus 4. All right, that would be so much harder to do if you squared this out and you squared that out and then you combine like terms. You'd eventually get a trinomial, and it wouldn't be a trinomial with a leading coefficient of 1. It would actually have a leading coefficient of 5. It would just be a beast. And yet it's actually very easy to factor, well, very easy to factor, if you recognize that the structure of it is very similar to the difference of perfect squares. All right, let's do another one similar to it. Let's take a look at exercise number 4. Which of the following expressions is equivalent to the expression 4x plus 1 quantity squared minus 16? All right, well, let me get rid of that little line so it's not kind of getting in our way. All right, what I'd like you to do, this is again very similar to the last one. I'd like to see if you can figure out which one of these answers is correct by structuring that using the difference of perfect squares. Pause the video now and see what you can do. All right, so what I see here is something squared. I'm not worried about what the something is, but it's something squared. And I can really look at this whole thing as 4x plus 1 squared minus 4 squared, okay? That means that all of this can now be factored into 4x plus 1 plus 4 times 4x plus 1 minus 4. I'm not going to include any parentheses this time because that 4 is a monomial, right? It's a single term, so there's no advantage to putting a parentheses around either the 4x plus 1 or the 4 here. Now it's just combining like terms. Should be simple enough. Here, nothing combines with the 4x, and 1 plus 4 is 5. And here, of course, nothing combines with the 4x, and 1 minus 4 is negative 3. And that's it. 4x plus 5 times 4x minus 3. Where is it? It's right here. Wait a second, Mr. Weiler, isn't that wrong because it has 4x minus 3 first? Not at all, right? It doesn't matter because it's multiplication and multiplication is commutative. It can go either way. All right, let's move on and do some more structural factoring. Now, sometimes we will need to factor trinomials whose degree, that's the highest exponent, remember, is equal to 4. All right, the state exams love these kind. Now sometimes, not always, but sometimes these trinomials come from the product of two binomials. So before we work on factoring trinomials whose highest power or whose degree is 4, let's first take a look at how they might arise in exercise number 5. Exercise number 5. Write each of the following products in standard polynomial form. Each will have a degree of 4. All right, so we're just multiplying two binomials together. And remember, we have like many different ways of doing that, including things like the area method, the FOIL method, the double distribution, the standard multiplication algorithm. Let's actually just do foiling on letter A and take a look at how it's done. It's very easy. Let's take a look. In letter A, we have x squared plus 8 times x squared plus 2. Right? X squared plus 8 times x squared plus 2. So I'm going to just do a little foiling here, right? First, outer, inner, last. So when I do x squared times x squared, I get x to the 4th, right? When I do my outer, 2 times x squared, I just get 2x squared. When I do my inner, 8 times x squared, I just get, well, 8 times x squared. And when I do my last, 8 times 2, I get 16. And just like I had when I had like linear binomials, now the only two things that will combine will be these two. 2x squared plus 8x squared is 10x squared, right? 2 ducks plus 8 ducks are 10 ducks. Same thing here. And we just get that trinomial. Now as a sneak peek for what we're going to be doing in exercise 6, we're going to be wanting to go backwards, right? So when we FOIL, we go this way. When we factor, we go that way, okay? Now what I'd like you to do is pause the video now. We've done so much work with multiplying binomials together. I'm hoping that these will be quick for you. Take a moment now and see what you get. All right, so I'm going to multiply these out very quickly using the FOIL algorithm. Right, I've got x squared times x squared is x to the 4th. X squared times 3 is 3x squared. Negative 6 times x squared is negative 6x squared. And negative 6 times positive 3 is negative 18. Be careful there. Again, just like before, those two will combine to be negative 3x squared and negative 18. All right. Letter C, same thing. Just making sure, okay. In here I have x squared times x squared, which is x to the 4th. Negative 3 times x squared was negative 3x squared. Negative 9x squared, and negative 9 times negative 3, again, always be careful with a negative times a negative. It's a positive. Positive 27. Here I have negative 3, negative 9 is negative 12. X squared plus 27. All right, so, yep, all looks good, right? Again, the reason that we want to go through this is that most of the multiplication that we did with two binomials, the two binomials were what were called linear, okay? A linear expression is one where the highest power is x to the 1st, okay? Highest power is just 1, all right? But these, the binomials are all x squareds, okay? And then they result, not surprisingly, right, in products that have x to the 4th. Now let's see if we can go backwards from this. Let's take a look. We can reverse these products to factor trinomials with a degree equal to 4. All right. Now let's see number 6. Consider the trinomial expression x to the 4th plus 3x squared minus 28. Write this expression as the product of two binomials, each with a degree of 2. All right, well, I want you to play the same game that we did before with factoring trinomials. I want you to think about two numbers that have a sum of 3 and have a product of negative 28, okay? Sum of 3, product of negative 28. Pause the video now and see if you can come up with those. All right, well, here we go, right? So two numbers that have a product of negative 28, right? And a sum of positive 3 will be positive 7 and negative 4, right? Positive 7 and negative 4. So I can now factor this. I need to be careful because I'm now going to factor it as x squared plus 7 times x squared minus 4. I have to make sure that I don't try to factor it as x plus 7 and x minus 4. X plus 7 times x minus 4 is not correct because if I multiply them out, I won't get this. Never forget that, right? You should always know whether this is correct because if you multiplied it back out, if it gives you this, it's correct. And if it doesn't give you this, it's not correct. It's really that simple. Now let's take a look at letter B though. One of the binomial factors in A can itself be factored. Which one and how? Okay, so I claim you should be able to look at these two binomial factors and go, well, that one I can break down even more. I can factor it even more. Pause the video now, identify which one you can factor, and then write down how it factors. All right, well, it's x squared minus 4, right? X squared minus 4 can be factored because it's the difference of perfect squares, right? And specifically, x squared minus 4 can be factored as x plus 2 and x minus 2. All right, it's as simple as that. Now, that being said, I claim you should easily look at this and know that it can be factored into this because we've spent time with difference of perfect squares. On the other hand, I don't want you to just take my word for the fact that that can't be factored, okay? So let's take a look at letter C. Why can the other binomial factor not be factored? Wow, the word factor shows up a lot, right? And that's because factor is both a noun and a verb, as we discussed early on in this unit. So let's take a look at why x squared plus 7 can't be factored. Well, I'd like you to think about it like this, right? I'd like you to think about x squared plus 7 as x squared plus 0x plus 7. Now, if you think about that, right, if I look at this, I'd be looking for two numbers with a product of positive 7 and a sum of 0. Now, there's only two sets of integers that have a product of positive 7. Those are 1 times 7 and negative 1 times negative 7, right? When I add 1 and 7, I get 8. Well, that's not 0. And if I add negative 1 and negative 7, I get negative 8. And that's not 0. So that's it, right? I don't have any other choices besides 1 and 7 that will give me this product. Even if I did, even if this was a 9 or an 8 or something that had multiple versions, right? There's no way that I would end up getting 0, right? The reason that I can factor the difference of perfect squares, again, thinking about this in terms of trinomials, right, is that I can find two numbers that have a product of negative 4 and a sum of 0. Those two numbers being positive 2 and negative 2, all right? So, can't do it in this situation. Now, letter D, let's get back to it, says write the original polynomial in completely factored form. Well, right, when we partially factored it, we had this. X squared plus 7 times x squared minus 4. And now we can finish it by then rewriting this as x plus 2 times x minus 2. And that's it, right? We can't do anything more than that. And it might disturb you that you can't do more with the x squared plus 7, but that's because it's what's known as a prime polynomial, right? A prime number is a number that cannot be factored other than writing it as 1 times itself. A prime polynomial is a polynomial that can't be factored. And remember, polynomials and whole numbers act a lot like each other. So if we've got prime numbers, we surely have prime polynomials. By the way, x plus 2 is a prime polynomial as well. It can't be factored. And x minus 2, it can't be factored either. Also a prime polynomial. Okay, so by the way, in summary, because this is pretty important, quadratic binomial factoring, that's a mouthful. A quadratic is something with an x squared, right? Something with an x squared is its highest power. A binomial is something with two terms. So quadratic binomial factoring, quadratic binomials of the form x squared plus a or x squared minus b cannot be factored except in the case of the difference of perfect squares. So if you have something like x squared plus 9, not minus 9, x squared minus 7 and x squared plus 15, none of those can be factored, whereas x squared minus 25, right, which is x squared minus 5 squared, can be factored. So the only kind of binomial things that you can factor with like an x squared minus a constant would be an x squared minus a perfect square, right? Something that can be rewritten as x squared minus something else squared. All right, let's keep going. So we got that same fact up here. Take a look at exercise number 7. Which of the following binomials can be factored? All right, only one of those could you factor. Take a look and circle which one you think it is. All right, well, it's number three. It's letter three. It's number three, right? And number three can be specifically factored as x minus 6 times x plus 6, right? That can be factored. In every other case, you can't factor it. And again, I want you to keep thinking about what would happen if you shoved a 0x into each one of these, right? X squared plus 0x plus 16. Right? That one's tempting. It seems like it should be like x plus 4 times x plus 4, but then there should be an 8x in the middle, right? If it was x plus 4 times x plus 4. X squared plus 10, that seems tempting. X squared minus 18 seems tempting because it's a difference at least, but 18 is not a perfect square, right? Right? There's nothing there's no two whole numbers, no two integers that you can multiply together to get 18 and add together to get 0, because they'd have to be opposites, right? Which means that 18 would have to be a perfect square, and it's not. All right, that being said, let's take a look at exercise number 8. Factor the expression x to the fourth minus 18x squared plus 32 completely. All right, what I'd like you to do is pause the video now and see if you can factor this completely. First, start off with just binomial, like trinomial factoring, where, you try to figure out the two binomials, and then take a look and see if you can factor either or both of the two resulting binomials. Pause the video now. All right, well, to begin, I look at it and I go, well, it's a trinomial, right? It's a trinomial. So I'm going to start with that kind of factoring. I'm thinking about two numbers that have a product of negative 32 and have a sum of a product of positive 32. I apologize for misspeaking there. A product of positive 32 and a sum of negative 18. Well, again, if they have a positive product and a negative sum, both have to be negative. All right. Now 32, naturally you might think 8 and 4. But the problem with 8 and 4 is that when I add them together, I get 12, right? And I need to get 18. So then I think negative 2 and negative 16. And that's my winner, right? Because negative 2 times negative 16 would be positive 32, and negative 2 plus negative 16 would be negative 18. So I end up getting x squared minus 2 times x squared minus 16, right? So this is my sort of first step in factoring. Then I look at x squared minus 2 and I think to myself, well, it's the difference, right? But the problem is 2 is not a perfect square, so I can't factor x squared minus 2 anymore, right? There's no two numbers that have a product of 2, right, or have a product of negative 2 and a sum of 0. No two integers, I should say. There are two numbers, but they aren't whole numbers. They're kind of ugly. Anyway, but I can factor x squared minus 16 because it's the difference of perfect squares. And in fact, I can factor that one as x plus 4 times x minus 4. This is a very, very common type of problem on standardized exams, right? They want you to look at it, they want you to recognize that it's a trinomial, so it can first be factored like this. Then they want you to look at those two factors and say, well, are either one of those the difference of perfect squares, right? Sometimes it can be both. You could factor something and get, something that looks like this, x squared minus 4 times x squared minus 100, right? And if you got that, well, then you'd be able to factor them both. That'd be x plus 2, x minus 2. That would be x plus 10, x minus 10. And you'd be off to the races. You'd have 4 linear factors at the end of that. Most of the time, it's just one of them that can be factored. And sometimes it's none of them at all. Sometimes you're done right at this step. All right, let's summarize. In this particular lesson, we didn't introduce really any new type of factoring. What we did say is that you have to be flexible with those three main types of factoring so that when you look at a rather complicated algebraic expression, you can recognize which type of factoring you can employ. Sometimes you'll have to use more than one. It's rare that you have to use more than two, all right? And oftentimes, the first thing that you're doing is maybe a GCF factoring followed up by either a trinomial or difference of perfect squares, or sometimes the first thing that you're doing is a trinomial factoring followed up by a difference of perfect squares, which is what we saw in those last few exercises. All right, we've got only one more lesson on factoring. It might be the most challenging of them all. We're going to be using factoring throughout the rest of this course though, so make sure to get really good practice on this on the homework. For now, I just want to thank you for joining me for another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.